Morning. Welcome to Krishna's classroom. Let us continue with our talk on the bounded linear functionals on normal linear spaces. Our objective is to look at the dual of the LP spaces. Now we recall the following. So let X be a normal linear space over R or C. So the field we take as either R or C, depending on which it will become a real vector space or real normal linear space or a complex normal space. Now consider a map phi from X to the field. Let me use K, where K is R or C, depending on whatever be the, where K is associated. Now we assume phi is linear. Phi is linear, that means phi of x plus y equal to phi x plus phi y, phi of alpha x equal to alpha times phi x. That is the usual definition of linear. Then is called a linear function. Now we are not assuming that x is finite dimensional. Therefore, we require some topology to work with on that. As I was explaining last time, this is essential when you go to infinite dimensional spaces. Therefore, on X we assume, let norm on X and the norm usual definition. This endows the space with a metric topology. We define the metric Therefore, now it's a topological vector space, so you can talk about properties like continuity, boundedness. Now we define what is boundedness. Phi is a bounded linear functional it's a bounded linear functional if there exists k positive such that modulus of phi of x for every x k is called the bound of bound of phi. Now look at phi. Phi is essentially a linear transformation from a linear space into another linear space because K is already a linear space. Okay. Therefore, it's a normed linear space. So it is from one normed linear space into another normed linear space. And you see that in K, the norm is defined by its absolute value. Okay. And therefore, you see that the norm of the image is less than or equal to k times norm of x for every x belonging to x. Then we say that phi is. And remember, I said it's a linear operator. It's a linear transformation. But this linear transformation is something special because the range is R or C. In that case, you give it a special name, namely linear functional. So phi is a bounded linear function on x bound by k. So this is the basic thing. Now what we mean by the dual space? Now consider all normed, all bounded linear functions so let us call this, so let us give a designation x prime. Now one immediately verifies that x prime is a normed linear space. First of all, it's a linear space. Why it's a linear space? You see that phi 1 plus phi 2 x prime. Now alpha phi belongs to x prime whenever phi belongs to x prime and alpha belongs to. So these are the usual properties of linearity. Now you can define norm of phi We'll define norm of phi. That means a norm on x prime by norm of phi equal to supremum of it could be equal to 1. This is a norm. Both x and x prime are there is an induced metric on x prime. There is an induced metric on x prime. So this is the, and x prime is a norm. X prime is called so that's the definition of the dual space. So X is the given normed linear space, X prime is the dual space, the space of all linear functionals. Now let us recall what we did yesterday. In our last lecture we have seen that if is a finite dimensional over K and X prime where X is a unique X such that xy for x belonging to x, and further this we have not verified last time, norm of phi equal to and there is an isometric isomorphism of of there is an isometric isomorphism of x to x prime, or x prime identified with x. In fact, if k is c, then this is a conjugate isomorphism. We said that alpha phi will be identified with alpha conjugate y. Okay. Now let me write xy equal to yi general conjugate. Now this is something which we have observed last time for the finite dimension space. For the finite dimension spaces, it is clear. In fact, you don't need this norm work with. You can otherwise all these statements hold. But the moment you go to infinite dimension spaces, you need a norm to work with. Now, where of course I have to make it clear that okay. So that's about the finite dimension space. So we are now moving into infinite dimension spaces. And especially we want to work on what is called LP spaces. Let on X. Suppose maybe even infinity. We are considering A. a whole bunch of cases together. Let Q be the conjugate of P in the sense that equal to 1. So this is a very crucial relationship. Now we define, look at, so we take X to be LP mu, which we define as a set of all F defined on sorry, the notations. This is okay. This is not okay. Set of all F. These are all complex valued functions defined on X such that you have integral here I think I have to caution it is not the same X that I am using earlier, but I am now talking about X. It's a measure space. So it's a measure space. You be a positive measure of X. Suppose this is true and this the conjugate number, and then you have result. Now you see that LP mu is a vector space. So norm the linear space with the norm one by B for 1 less than B, and norm F infinity equal to norm of so these are the definitions of norm P and norm. Okay. So these are the different cases. This is the case corresponding to Calicut. So this is the space on which we are working. Now we already know a very basic inequality for them. By Holder's inequality, if G belongs to LQ, where of course LQ mu, and if phi G is the linear functional on LP defined by FGD is a bounded linear functional on LP mu of norm one by 3. So this comes like this, So you see, here we have two spaces now, LP and LP. Okay. So we pick a element from LP. So we have two spaces, LP and LP. Equal to 1. And we have phi G defined by mu. Now phi G is sorry. Phi G is a normed linear space. So it's from that normed linear space to it's a K. It's a linear band. 5G is linear. Is it bounded? Yeah. See, 5G is a linear, in fact 5G is a linear functional. But first of all, is this well defined for Fg belonging to okay? We by holders inequality phi F, the absolute value of this is less than or equal to integral over x is a very general result. Worth looking at how this inequality is arrived at. Therefore, you see that this is a so because of this, now you see that norm of that is you can write like this mod norm of okay, and this is true for every P F belonging to LP. So we can designate this, right? Then so the inequality assures that if G is in LQ, then there is a K such that this inequality is true for every F belonging. Okay, now this is true. Therefore, what we observe is that determines a bounded linear functional. See, that's why the conjugate relationship is important. For instance, if when p equal to 2, then q is also equal to 2. So then these two spaces, L2, this would become L2. But otherwise they separate out. And these are all, those who have done about Banach spaces, you will see the difference. And when you take L2, it can be made into a Hilbert space. So these are quite a lot of things about the geometry. Okay. Therefore, what does this say? This says that if you take the unit ball in LP, that is the norm of then is the unit ball. Then it is mapped into a ball of into a ball of radius. What is the radius? Two. Okay. I think I just use another notation here, yeah, so that no confusion. Okay. So you see, it's a map from LP to K, right? And the unit ball in LP is now goes into a ball in A in K. And what is the radius of that K? That ball. The radius of this ball is, in fact, norm GQ. So this is what you get, the geometry of this map. That means this is the following. This is your, take the unit ball here, okay, and then this is your K. K is either an interval, either the real line, or this is K equal to C or R. If it is C, then this is the picture that you have. This gets mapped under by G, maps an F here to by G. Okay. If it is R, then it's an interval with radius norm G That is the Q norm of G. Okay, right. So that's the result that now we are going to now the question that you ask is this. Is the dual of this equal to or 1? This is the question. Okay. Now you see that this question is always, in the finite dimensional spaces, just the space itself becomes part of it. Now, if you are endowing the Rn with P matrix, then Rn prime, that is the dual of that, will have metric corresponding to that given by Q metric. Okay. That is not very relevant because we are working in finite dimensional spaces. But if we are working in an infinite dimensional spaces, this becomes quite relevant because you know that LP is not equal. So in general, Q, that's one observation. Second observation is that the objects in these two spaces LP and LQ are different. Not only that, they are also the two spaces are different. Okay, right? Two spaces are different. LP may not, general LP is not equal. So the question that we ask is the following. When or are there situations where LP prime is that is the dual is equal to okay. Now it turns out that it's very interesting. It turns out that if 1 less than infinity, then this identification we can, okay, but this is not true when P equal to infinity. But this result is not true when P equal. infinity. Now we shall give a, so this corresponds to the case that is equal to 1. So the question that you are asking is because you know that when p equal to infinity, then q equal to 1. Right? So this is the broad question that you are asking. Now we are going to first of all answer this question. We actually show that this is not possible. Now the example that we or the proof we give is this. Okay. So let us take the following example. Let be the interval 0 and mu equal to m, the Lebesgue measure. Then we are asking, then the question is L infinity dual of this with the Lebesgue measure. Okay, with the Lebesgue measure. So consider the set of all continuous functions on the interval 0, 1. The real is enough. Okay, let us work on the real space. Okay, the space of all continuous on the interval 0, 1. Of course, the measure is the Lebesgue measure. Okay. Now what you have, we clearly observe that C01 is properly contained in with Lebesgue measure. With Lebesgue measure. Okay. So you are looking at all continuous functions on the interval 0, 1. These are all L1 functions on the interval 0, 1. This is L1 space is integral over mod f dm less than infinity. So such functions. As I said, this is a proper containment that you have on C01 is properly contained in L1. Therefore, sum f tilde not equal to 0 I'm taking this L infinity 0, 1 and f tilde does not belong to 0. It's not a continuous function. That is clear. Okay. What is this? This space, this f tilde, you can choose a discontinuous function on the interval 0, 1. A bounded discontinuous function. Example, discontinuous any function on which has discontinuity. At some points, so at half you can have a discontinuity. Okay, and the function need not be it can be 0 from on the interval 0 to half, and from there on it should be taken as 1. Okay, right. For example, take tilde is the characteristic function of the interval half, which is a discontinuous function. Such a function exists. Let m be the complement of f tilde is the notation for that. The space spanned by f tilde. 0, 1. Okay. So M equal to the set of all zero 1 where G is not equal to some alpha F tilde for alpha belonging to okay. Then clearly then we have the following. When I say complement, this is what I equal to M plus N. Okay. Right? So C that is also true. Let us take this. Now take any F alpha plus F where alpha is constant. Define lambda F to be equal to alpha. Okay. And extend on the whole of L infinity zero 1 linearly. So this is the general expression for this. It's an element G belonging to M plus this. It's linear. So once you get this, it is defined as this. So every element can be. So this implies that or that is the C01 is a part of it. Okay, therefore to have this, keep this in mind. Now the question that you ask is this: is Does there exist a G belonging to L101 such that equal to integral 0 to 1 FGP. If so, you see that you are finding identifying lambda with G. Okay. Now we prove that this does not exist. This may not be true. Okay. Now you see that lambda F zero. What does this mean? So if F belongs to C01, this implies now choose identically equal to 1. Hence integral 0 to 1 G d mu equal to 0. Like dm. This is the Lebesgue measure. G dm equal to 0. What does this mean? This implies G is equal to 0 almost everywhere on G is equal to 0 almost everywhere on 0, 1. G is equal to 0 almost everywhere on. What does this mean? That is norm of G equal to 0. Norm of the L1 norm of G equal to 0, or G is the 0 element of G is the 0 element of L1 0. Now you take And this implies, see, where did we start with G? Now we shall take lambda f t equal to integral over 0 1 f g dm. Okay, that's the thing. Let lambda be a what do you have? Lambda of lambda of what is it? Equal to alpha definition. That means alpha, where alpha can choose lambda f equal to integral 0 to 1 dm L infinity, and this we have seen, and this is equal to 0. So we are able to can find a linear function on L infinity which is not by definition however if there exists a G belonging to L1 mu such that yeah, which vanishes, okay, which implies equal to 0. So there are these two things do not, hence therefore not every has a representation Therefore, not every lambda. That means zero. That is the dual of L infinity is not equal to L. So that is the case. So there are situations where, so we have proved that L infinity this is the conclusion. However, we shall prove later that, so the question is, so what we prove is, whenever so this is one of the major theorems that shall prove that this is here same, and with some restrictions. We shall have L1 this can be identified. All these are not equal, actually you are identifying. Okay, so this is the major analysis that we have. So we have now we make some assumptions and then try to give the statement of the theorem, or I will give the statement of the theorem in my next lecture and then start. So I think this is a nice place to stop. Okay. So the major question that we are asking is LP mu the dual of L same as L mu? In general, it is true whenever 1 less than 10. But when P is equal to 1 or P equal to infinity, there are some problems. And we have shown that when P equal to infinity, then this is not true because we have given an example. And when P equal to 1, then with some restrictions, we are able to come to the conclusion. So this will be the main theme of the lecture that we do. So we will be exploring what are the dual spaces of, okay. Now, with this uh, remarks, let me conclude the lecture for the day. Thank you very much.